Hey guys, welcome back to another AP Chemistry video. Today we're talking about Unit 5, Kinetics, and we are getting pretty close to the end of the semester, so we might start feeling a little disorder, a little overwhelmed, right? Because it is a pretty busy time of the year. So make sure we're taking some time for ourselves, take some mental health breaks, right? If you are feeling overwhelmed or have any questions about your classes, make sure you go talk to your teachers before the semester ends, all right? But so this video will be our last video for the semester. Okay, Unit 5 will be the end of the semester. Then we'll go on winter break, and then we have 4 more units to finish off our lessons. Okay, so we're almost there. We're about a little more than halfway done. All right, so for kinetics, our vocabulary, we'll talk about collision theory. We'll talk about some reaction diagrams with intermediates and catalysts. We'll talk about rate determining steps with the rate law and orders. And then we'll talk about some equilibrium and some half-life. All right, so for our reaction graphs, or in reactions in general, right, we have 3 main questions to answer. The first one is, will it go? Will it happen? That is answered by thermodynamics, which we'll talk about in Unit 6, and kinetics. The second one is, how far will it go? We've already answered that with stoichiometry, right? We can determine how much of our reactants will be used, how much product we'll make. And the third one is, how fast will it go? That again is kinetics. Okay, so to answer these questions, one of the things we use is collision theory. Okay, so collision theory is that molecules must collide. We have to have a collision for a reaction to happen. The second part is that they must collide with sufficient energy. Okay, and remember when we're talking about energy, we're talking about that activation energy going from the reactants to the top of the peak. Okay, that curve there, that's our activation energy, how much energy is needed for the reaction to happen. And the third one is that they must collide with the correct orientation. Okay, so on our image on the right here, on the top right, we have 3 scenarios. And the first one, our molecules are colliding head-on, and these inner molecules are going to react, but the outer ones are isolated, so they won't react. Okay, so that one is not a correct orientation, so the reaction won't happen. For 2 and 3, we start off the same. So we have the correct orientation where one of these will react, and then it'll kind of curve and react with the other molecule. So we get 2 reactions there, or we get 2 products, I mean. Okay, so both of these have the same reaction happening, the same mechanism. But you'll see on the right here, only one of them forms the product, one of them bounces off. If it's bouncing off in 2, that means we don't have enough energy. Okay. For 3, we have enough energy and we have the right orientation, so the reaction happens. So for collision theory, we need all 3 parts. We need the molecules to collide, we need to have enough energy, and we need to have the correct orientation. Okay. So some parts that affect, or some factors that affect reaction rate is surface area, right? So if we have a higher surface area, if we have smaller pieces, we're going to have more collisions. So that increases the rate. If we increase temperature, our particles are going to have more energy. If we increase the energy, we're going to have a higher reaction rate. If we increase the concentration, how much we have, how many particles, right? More particles, we said, is more collisions. If we have a catalyst, so catalyst can do one of 2 things. It can either put the molecules in correct orientation, so it can hold our molecules together, or it can lower the energy of the reaction, the activation energy. But either one of those, we said, increases the reaction rate. They're part of collision theory. And then with gases only, for pressure, a higher pressure increases the reaction rate because the particles are moving faster, right? They have more energy there because pressure affects temperature. Okay, so you'll notice all 5 of these have to do with collision theory, right? You're increasing the collisions or you're increasing the energy. Okay, and these graphs down here kind of help you visualize it. This one on the left is for temperature. The blue line is our higher temperature. The red line is our lower temperature. You'll see the blue line reaches the product, total products first, because we have a higher rate of reaction. So what rate means is we're not making more products, we're just reaching the products faster, right? So both of these lines will end up at the same point, the same plateau. The graph on the right, we're looking at catalysts. So a catalyst just decreases that activation energy curve. Okay, So for these reaction graphs, we need to know each part of it. So we're gonna label this graph. I'm just gonna put letters. You can do letters if you want, or you can write out the whole thing. But I don't have enough space to write out the words, E, F, and G. Okay, so we start with our reactants. Remember, reactants is the start of our reaction. It's what we have at the beginning. Our product is what we make at the end. So reactants at the beginning, products at the end. C is the intermediate. This is a temporary substance formed and used in the mechanism, right? So this is in the center. So we form it after the first step, and then we use it before the last. So it's gonna be that center step there. If you have a little dip in the center, that's your intermediates. Okay. D is a catalyst. It's something that we said that stabilizes the transition state, right? This is something that helps with activation energy, and it's at the beginning and the end. So it shows up at the beginning, so I'm going to put at the beginning with the reactants. It's used throughout, right? It's holding the pieces together, and then it comes back out at the end. It's not used up. Okay, so this happens at both the reactant and the product side, or it's shown there. Okay, the transition state or the activated complex is already written in. That's our AC1 and AC2. Okay, so those are written in for you there. That is the point where our bonds are starting to break and they're starting to form new bonds. Okay, so this is like a middle step where before our new bonds are formed, before our products are formed, we're starting to break the bonds and we're starting to form new ones. Okay, and this is each peak. So each time there's a peak, you have a different activated complex. Okay, and this isn't one of the things listed here, but remember we have that activation energy going up to that activated complex. All right, and then the last two are the slow step and the fast step. These will have to do with the rate, which we'll talk about here in a minute. But the slow step is going to be your tallest peak. The fast step is your shortest peak. Okay, so our tallest peak here is AC1. It's going to be our slow step because it needs more energy, so it's slower. And then AC2 is our fast step, so it's going to be G. Okay, so that's how your graph should be labeled. Okay, and just as a note for a slow step and fast step, when we say the tallest peak, we're not talking about how high it is on the y-axis. We're talking about the activation energy. So you'll see here from the reactants to AC1 and then from the intermediates to AC2, that is the distance we're looking from. So from the reactants to AC1, that activation energy is going to be larger. So that is why it's a slow step. That's the tallest peak. Okay, so even if you have something like that, right? Even if our second peak is taller on the y-axis, it does have less activation energy. Okay, so the activation energy is what determines what the tallest peak is. All right, so let's look at a question with this. So from understanding understanding the parts of a reaction, the diagrams, we can determine which diagram fits a reaction. So we have this reaction here. We have chloride gas atoms with ozone molecules in the upper atmosphere, and they react according to this mechanism. So we have two steps. We have 1 and 2. The first one is a slow step. The second one is a fast step. Okay. We are also given a delta H value. Remember, delta H is our enthalpy. This we'll talk about with thermochemistry and unit 6, but you've talked about it in either advanced or on-ramps chemistry before. Remember, if you have a negative number, that means you're decreasing the energy. So on our graph, it's going to be going down. So the reactants are going to be higher than the products. Okay, so let's take this step by step. Let's start with the delta H, our enthalpy. Our enthalpy should be negative. So the only graph here that is positive, right, on D, we have an upward slope. That's not going to be the correct answer. Okay. The second thing we're going to look at is we said we have 2 steps. So we should have 2 peaks. A only has 1 peak, so that's not going to be the correct answer. So we're down between B and C. This is going to be based on the slow or the fast step. So step 1 should be the slow step. Step 2 should be the fast step. So if we look at the distance of the activation energies, for B, our first one has a bigger activation energy than the second peak. For C, our first peak has a smaller activation energy than the second peak. And remember, a slow step should have the bigger activation energy. It needs more energy to happen, so it's slower. So our answer here is going to be B, because our first step is the slow step. And then for this question, which of the following will increase the rate of the reaction? I'm going to let you guys think about this. So if you need to pause the video, take a minute, use your notes if you need to. This was from the first few slides talking about the rate of reactions. But our answer here should be B. Okay, so make sure you understand the reason for each of these though. Don't just put B and move on. Make sure you understand this question. Okay, because all the questions are modeled after AP questions. So you might see something similar to this again. All right, so moving on to rate laws. When we talk about rates, we're seeing how each reactant affects the reaction process. Okay, so if we're using this equation as an example, if we have 2NO2 gas plus F2 gas goes to 2NO2F gas, right? If we double NO2, so for the first bullet point here, if we double NO2, and the rate also doubles, we have the direct proportionality, right? What happens to one also happens to the other. So in that case, our rate is proportional to NO2, and you'll see here the power, the exponent, is a 1. So that's what we call first order. For the second bullet point, if we double NO2 and the rate quadruples, that's quadratic, right? What we do to one, the square of it happens to the other. So you'll see our proportionality is now squared. So that's second order. And then for the third bullet point, if we double NO2 and nothing happens, it's unchanged, our exponent is now 0, that is 0th order. Okay, so these exponents, the powers, we call those our orders, and they're with respect to the reactant. They tell us what's happening. Okay, so if we have NO2 to the squared, second order, that means we have a quadratic proportionality. Okay, and the orders are going to be given by stoichiometry or elementary steps. We'll look at each of these here in a minute, but our rate law is going to look like this. It's going to be in this equation. So where R is the rate, K is our rate constant, which we'll talk about on the next slide. And then our A and B are our reactants. The X and the Y are going to be our orders. Okay, so that's what the rate law looks like. Depending on how many reactants you have, you might have A, you might have A and B, you might have A, B, and C, or so on and so forth. Okay. So with our rate constant K, we need to figure out its units. The units aren't set for this. The units for our rate are as molarity per second. Okay, so we have a molarity per second is equal to some units for K, and then whatever else we have. Right, so if it's 0th order, that means we have something here to the 0th power. So it essentially it's not there, right? So anything to the 0th power is 1. So at 0th order, the units for K is going to be the units for rate. It's molar per second. Okay, for this first order, right? If we have something here, if we have 1 molar there, then if we need to find K, we need to divide by what K is with. So if we divide by molarity, K is just per second. Okay. For second order, if we have molar squared and we divide by molar squared on both sides, we'd get K being molar to the -1, second to the -1. Okay. And you'll see a pattern here, right? If it's first order, it's molar to the 0, second order molar to the -1, third would be molar to the -2, fourth would be molar to the -3. So you can either memorize that pattern or you can just figure it out by doing algebra with the units. Okay. All right, so this table here summarizes a few things for us. So again, we have our rate equation on top, so we don't forget that. But we're going to start with the molecularity. Molecularity tells us how many molecules we have. So unimolecular means we just have one. Bimolecular is two things, whether there's two of the same or two different things. Termolecular is three. Okay, so if we have three of the same things, three different things, whatever it is, as long as we have three things there, that's termolecular. Okay, so our elementary steps is that step in the reaction. So we saw, let me go up real quick to an example, right? we had these two steps. These are elementary steps. Okay, so that's what it means by that. So based on this elementary step in column 2, we have our rate law, and you'll see that the exponent is based on how many you have. So on the first one, we have a to the first power because we only have one a. The second one, we have a squared because we have two a's. Okay, so that's based on stoichiometry there. Okay, and then we have our orders. So depending on the exponent, we have our order with respect to a, b, or c. The overall order. Okay, so the overall order, all you're doing is just adding whatever is in the orders together. So if you just have one thing, it's the same. If you have more than one thing, you add them together. Okay. So that's how you get the overall order. It's just adding the exponents together. Okay. So looking a little bit with the equilibrium side of things, right? When we have a reaction happening, the products are going to be increasing until they reach a plateau, until they reach equilibrium. The reactants are going to decrease again until they reach the plateau. And it looks like this starts to curve up. That should actually not curve up. That should just be a plateau, straight line there. Okay. So when the slopes approach 0, so at that point that the slopes start to plateau, that's when we have equilibrium. Okay. That's when the rates are equal. Okay. And so when we're talking about rates, the slope of the curve is the rate. We can either have an instantaneous or an average. You won't have to calculate the slopes really for AP chemistry, so we're not going to worry too much about that. Okay, so let's go ahead and start talking about our rate laws and start solving for them. All right, so we have two types of mechanisms that we'll solve for. The first one is we have a slow step, and that slow step is our rate determining step. This one's really simple. The second one is we have that fast equilibrium. Okay, a fast equilibrium is a little more complicated, but a fast equilibrium means that we can solve for the rate law by using equilibrium expressions. Okay, so let's start with this example here. If we have the rate law is R equals K NO2 squared for this reaction here. Okay. Do the following elementary steps match the reaction? Okay, so first we're going to determine, does it match stoichiometrically? Okay, so does the stoichiometry of the reaction match our steps? So if we just take our steps, if we have something on opposite sides, they're going to cancel out. If they're on the same side, they're going to add together. Okay, so we have NO2, NO2, NO2. We have 3 of those, but one is on the right side. So it's going to be 2NO2 minus the one from the right, just gives us a single one. Okay, so that gets rid of our NO2s. For NO3, we have one on either side, so we're not going to consider that. For NO, that is on the right side only. CO is only on the left side, and then CO2 is only on the right side. Okay, so does our overall reaction match that reaction there? And it does. So stoichiometrically, it does match. Okay, then does it match our rate law? So does it match our rate law here, the R equals K NO2 squared? So for that, we're going to look at our steps. We have a slow step and a fast step. If we have a slow step and a fast step, and these arrows are just going in one direction, then we're just going to look at a slow step. So our slow step here, the reactants, let me erase it so it's easier to see. So our reactants for the slow step are NO2 and NO2. Okay, so we have NO2 squared. And remember, those brackets just means concentration. Okay, so the concentration of NO2 squared. And remember, when we're putting the rate equation, it's rate equals the constant times our reactant, so NO2 squared. And that does match. So since it matches stoichiometrically and it matches the rate law, these elementary steps, the step 1 and step 2, do match for this reaction. So the answer here would be yes, it does match because and you'll explain stoichiometrically and the rate law. You'll bring both of those into explanation. Okay, let's do these two as well. Okay, so for these below, we're going to determine the overall reaction, determine the rate law, and then identify catalysts or intermediates. Okay, so let's start with number one. For number one here, we have these two steps. Okay, so start with stoichiometry to determine the overall reaction. Okay, H2O2, we have 2 on the left side, so we have 2 H2O2. I minus, we have it at the beginning and we have it at the end, so we're going to cancel those out. IO minus, again, it's at the beginning, it's on both sides, we're going to cancel those out. So H2O2 is going to go to, we have 2 H2Os, and we have 1 O2. Okay, so that's our overall reaction. Our rate law, so let me erase this, because we don't need that anymore. Our rate law is going to be based on our slow step. Okay, so our reactants are H2O2 and I minus. So rate equals K times H2O2 times I minus. Okay, so if we're talking about this rate law, they're both to the first power, so our overall order is going to be a second order. All right, and then the third part is identify catalysts or intermediates. Okay, so we have to go back to our definitions for catalyst and intermediate. Remember, we said a catalyst is at the beginning and end. The intermediate is in the in-betweens. So catalyst is at the start of 1 and at the end of 2. It's at the very beginning and the very end. The intermediate is at the end of step 1 and the start of step 2. So it's right in the middle. Okay, so if we look at this reaction here, we have an I minus that's at the very beginning and the very end. So our I minus is our catalyst. And then we have an IO minus that's at end of step 1, beginning of step 2. So IO minus is our intermediate. Okay, so that's all we're doing for this. All right, so I want you to try to do this second one here. Okay, the second one's going to be very similar. This actually, I think, is that same equation we just did up there. So you can, oh, it's not the same actually. It's a little different. Sorry. The first step is the same. Okay, but you're going to, for the second one here, you're going to do the same 3 things. You're going to first determine the order or the reaction by doing stoichiometry. Then you'll write the rate law. And then you determine if there's catalyst or intermediates based on those standards. Okay? So work through that. If you need to check your work, come ask me during class. But you should be able to do that at this point. All right. So the other part of this is the fast equilibrium. This one's a little trickier. Okay? So for fast equilibrium, you'll have whatever your step is, it'll say fast on the right, and in your step, the arrow is not going to just be an arrow going to the right, it's going to be an equilibrium arrow. It goes both forward and backwards. Okay, so if you have that equilibrium arrow and you have the fast, then you're going to do the fast equilibrium. Okay, so the steps for fast equilibrium is you're first going to identify your fast equilibrium step and your slow step. You're going to find both of those steps. You're going to find the rate law from the slow step, just like we've been doing, just R. So that would just be R equals K, and then your concentrations from your slow step. The step 3 is kind of where it gets confusing, 3 and 4. For 3, you're going to set the forward reaction of your equilibrium equal to the rate of the reverse reaction. Okay, so you're going to set up 2 rate laws and set them equal to each other just for the fast equilibrium. Then you'll solve for the intermediate and cluster your terms. Okay, so those steps can get confusing. We'll work through that together right now though. Okay, so if we have this here, There's a lot of steps. But remember, our first step said we care about our fast equilibrium. So we have fast with that equilibrium arrow, and our slow step. Okay, so steps 3 and 4, they are fast steps, but they don't have the equilibrium. So really, we don't need those for this question. So if you want to erase those, you can, or cross them out. We only care about steps 1 and 2 here. Okay, so our second step from the fast equilibrium slide was derive a rate law from our slow step. So our slow steps here. Our rate law is rate equals K, and then we do our reactants. Okay, so there's no coefficient, so we don't need any powers. But our first reactant is Hg, Cl2, C2O4. Let me write this somewhere else so it's a little more room. Okay, so we have our first reactant times our C2O4 2 minus, second reactant. Okay, so our slow step rate law is up there. Our third step is to set the rate law of our forward. So our forward reactions, these are the reactants, equal to the rate of the reverse. So the reverse reaction, we're going the other way. So our product is the reactant there. Okay, so the forward reaction, we would have rate equals K times our reactant. I'm going to put K1 because it's our forward. Or let me do KF. KF for our forward. Then our reactants for step 1 are HgCl2 and C2O4 2 minus. Okay. For the reverse reaction, so rate equals Kr, K reverse, our only reactant there is HgCl2 C2O4 2 minus. Okay. So we can combine those, so rate equals rate. So if we combine the two of those, we would get, or not combine, set them equal to each other. We'd get the forward reaction KFHgCl2 C2O4 2 minus is equal to our K reverse times HgCl2 C2O4 2 minus. Okay, so step 3 from our, so that was step 3 from our previous slide, talking about the fast equilibrium. Step 4 is solve for the intermediate. So the intermediate is going to be what shows up at the end of step 1 at the beginning of step 2. So that's our HgCl2 C2O4 2 minus. So we're going to solve for this term here. To do that, use divide by Kr on both sides. Right? So our intermediate is equal to what is on the left here now. And then step 5, or sorry, the second part of step 4 is substituted into the slow step. So we're going to take what we got here for intermediate, and we're just going to plug this in to the slow step. Okay, so let me go down a little bit. So our rate law was R equals K Hg Cl2 C2O4 2 minus times the C2O4 2 minus. Okay, so that was our rate law from the slow step. Then we're going to plug this into here. So our rate, our R, is equal to K. Then that whole thing is Kf over Kr C2O4 2 minus. And then don't forget to bring this back down. We still have a C2O4 2 minus at the end. C2O4 2 minus. And then we just cluster terms. So all our K's will bring together to make K prime. So R equals K prime. And then what we have left is 2 of the same thing. So those two combine to make C2O4 2 minus squared. Okay. So a few steps. Sorry, I got a little messy on my side of things. but we first found the rate law of the slow step and red at the top. Then in yellow and pink, we did the forward reaction and the reverse reaction of our fast intermediate. In blue, we solved for our intermediate based on those two. So to set them equal to each other, solve for the intermediate. And then in black on the bottom right, we plug that in to our slow step and just solve for the rate, clustered our terms. All right. So this one is a little more complicated. You do need to know how to do this though. Okay, so make sure you do some practice with this. You'll see some of this in your practice packet. But if we need help, make sure we ask questions. Okay. The second way we can talk about rate is experimental determination. So what we talked about so far, we haven't had any numbers. Now we're going to use some numbers. We're going to do some things with experiments. Okay. So we're doing it with the overall reaction and not individual steps. And we're going to use data and not stoichiometry here. Okay. So the rate laws are still the same. These equations on the right, I believe, let me check real quick. I believe they're in your research page with all your equations. So on the back with kinetics, you do have all three of those available to you. So you don't have to memorize those equations. Okay. You do, however, need to know which one is first order, which one is second, which one is third. Okay. So if we just have the concentrations on their own, that is 0th order. If we do ln of the concentration, that's our first order. And then 1 over the concentration is our second order. And I'll show you why that's important here in a few slides. Okay. All right. So what we're going to do with this is we're going to have a set of data like we have in this table here. And we're going to determine individual parts by doing something like this. We're going to set our rate law over a second rate law. So 2 different trials. Okay. That way we can cancel out some terms and we can find some unknowns. Essentially what we're trying to find is those exponents. We're trying to find the order of the reactions. Okay. So what we can do is we are going to leave one concentration changing and the rest constant. So the reason we do that, so if we do, let's see. So 1 changing, the rest constant. Let's do 1 and 3. Okay. So 1 and 3 leaves A constant and B is changing. Okay. I'm going to put 3 over 1 just to make the math a little simpler. But if we do 3 over 1, we would get, following this equation here, so rate equals K times the concentrations. Our rate for 3 is 2.0 times 10 to the negative 4 equals K. Concentration of A is 0.10. I don't have the exponent, so I'm just going to put a lowercase a there. And then concentration of B is 0.30. I don't have an exponent, so a lowercase b. Then our trial 1, the rate is 2.0 times 10 to the negative 4. K stays as K, lowercase k. A there is 0.10. Exponent is A because we don't know that. B is 0.10. The power is lowercase b because we don't know that. Okay, so here we can cancel like terms. K over K is 1. 0.10 to the A divided by 0.10 to the A is also 1, so we can cancel those out. And then we're left with what we have. So on the left side, these also cancel out to make 1. So 1 equals our 0.30 to the B divided by 0.10 to the B. So we have 1 equals, if we divide those two, 0.30 divided by 0.10, you get 3. And then we still have that exponent of B. So 3 to what power gives us 1? Well, 3 to the 0th power always gives us 1. Anything to the 0th power is 1. So we know B is equal to 0. Okay. So we know that our exponent for B is 0, to the 0th power. Okay, I'm going to erase this. And then we're going to do the same thing, but for A. Okay, So for A, you can either do what we just did, find one that is changing for A and then B is staying the same, or you can really pick any of them because we know B now, we can solve for the number there. But it's easier when it does cancel out. So for it to cancel out, we're gonna do 2 and 3. Okay, so if we do 2 over 3, we have the rate, so of 2, 6.0 times 10 to the negative 4 equals the concentration of A to the lowercase a power times the concentration of B to the 0th power divided by rate for 3 is 2.0 times 10 to the negative 4. Oh, sorry, I forgot my K in the first one. K times the rate of A is 0.10 times 10 to the A, or sorry, not times 10, just to the A. And then B is 0.30 to the 0th power. Okay, so again, our K's cancel out. They always will for this. Our B term cancels out. And then we're left with, on the left here, 6 divided by 2 is 3. So that leaves us with 3 is equal to, and this for A terms, 3.3 divided by 0.1 is also 3. So 3 to the A power. If our numbers are staying to the same, that means our exponent has to be 1. So we know A is to the 1st power. Right? So we have our powers, our orders for each reactant. So we can write our rate law. So rate is equal to K, A to the 1st power, B to the 0th power. Okay. And remember with your powers, if you don't want to write the 1 for 1st power, you can just write it as such. And then you can leave the B out because it's to the 0th power. Okay, so either of those would be acceptable. All right, so from this data, we found our rate law, and then our overall rate, right, if we add those together, 0 plus 1 is 1. So we have our rate law, and our overall rate for the reaction is 1. Okay, so that is all we are doing with this. We can do it, or I'm going to leave this one for you to do. Okay? So this one is the same thing. You have a set of data. This is actually the same one. Did I did not change out the numbers here. I will change out this, so you can find that in the slides. Or let me just, yeah, I'll just change that out. Find that in the slides. It will have an A, B, and a C term in the tables. Okay. And you should get as your final answer, rate equals K, A to the 1st, B squared to the 2nd power, and then C to the 0th power. Okay. So I'm going to change out this table, use a table in the slides, not in this video, to answer that question there. Make sure your answers line up with mine. Okay, let me make a little note of that real quick. Okay. Oh, that's the one. Okay, so ignore this slide here. This comes down here. Okay. And then you can just ignore the slide, because that's what we just did. Okay, so for this set of data, you should get this rate law. So make sure you work through that. If you need help with this, let me know. This one does have 3 variables, A, B, and C. So be smart with what you figure out first. Okay, see where things can cancel out through multiple of them, not just one. Right, so start with 1 and 3 because your A's cancel out and your B's cancel out. So you can start with C there. Okay. All right, so moving on to talking about graphing. So talking about the graphs for these. This is why I said knowing For 0th order, just A. First order is ln of A. Second order is 1 over A is important because what they can do is they can just give you the graphs and tell you to determine if it's first, 0th, or second order. And you determine that by the y-axis there. So based on what's on the y-axis, that tells you the order of the reaction. Okay, so whichever one of these comes to be a straight line, or whichever one has the best correlation, that is your order for the reaction. All right, so an example of that is if you have data, you can actually graph this data and figure out what the rate of reaction is, right? So if we have this data up here, we have our times going from 0 to 300, and we plotted our concentration with it. So we have times and concentrations. Okay. Our 0th order would just be our concentration versus time, as the numbers are. First order, we need to take the ln of the concentration first, then plot that versus time. And then second order, we do 1 over the concentration, then plot it versus time. And what this looks like is it'll look like this. So at the top here, I have my times. On the left, I have a column for NO2, the concentration. My column C is ln of the concentration, that's my first order. And then column D is 1 over the concentration. That's my second order. Okay. So for each of these, I put either the concentration, ln, or 1 over the concentration on my y-axis, my time on the x-axis. So for the first one, you can see my r² value is 0.931. That's for 0th order. For first order, the second graph is 0.982. And then for second order, my third graph, it's r² equals 1. So r² equals 1 means it has the best correlation. So from these graphs, we know that our data, what we had here, this is ultimately going to be a second order reaction. Okay, and you can make those graphs using either your graphing calculator or using Excel, spreadsheet, any of those. Remember, on the AP test, you won't have access to those. You'll just have access to your graphing calculator. So get used to making graphs through that. You shouldn't see a question like this on the AP test though, but I want to make sure that we're prepared for it just in case. All right, so just looking at the data, determining, making the 3 different graphs, whichever one has the best correlation, that is the one that is the correct order, okay? And again, I showed you these 3 up here. The way they'll show it on a test is they'll give you 3 graphs, right? And they'll give it to you with the concentration, ln of the concentration, and then 1 over the concentration. And it'll be obvious which one it is. The other ones will be curved. Okay, so only the straight one is the one that is the correct answer. Okay, so those are the graphs that I just showed you that I made for that data plot. Okay, and then our last topic for these notes is half-life. Okay, half-life, we do not have a lot for it, but there are a couple things we need to understand. First, the definition for half-life. Half-life is the time, so it's in time units, for half of the amount of substance to react or decay, right? So this can be used for nuclear chemistry. It can also be used for radiological dating, okay? So for half-life, we have 3 different equations. The only equation that's on your reference sheet is the first order one. So half-life, T1 half, is 0.693 divided by K. All right. The 0th order and second order also have equations, but they're not on your reference sheet, so I don't think you're going to have to do those on the AP test. I don't remember how to put into practice though, so you might need to still have those equations, but you can use what's on here. You don't have to memorize them. Okay. So an important factor with half-lives is for first order reactions, if your half-lives are an equal amount of times. So the length of the half-life is constant. So our first half-life takes about, 7 seconds. Second half-life happens at 14, third is at 21, right? Each of these is 7 seconds long. If that is constant, then it is a first order reaction, okay? If it is not constant, it's not a first order, but if it's constant, it's first order. So it's one thing we need to understand with this. The second part is just doing the math. Okay, so let's do these two questions together. If we have the decomposition of H2O2 to H2O and O2 follows first order kinetics with a rate constant of 0.0410 minutes or per minute at a particular temperature, what is the half-life for the reaction? So we know it's first order. We can use that equation to T1 half 0.693 divided by K. And we have K, so we can actually plug that in. So K is our rate constant, that's 0.0410. Okay? And that's per minute on the bottom there. So if we do that math, if we divide the two of those, we get 16.9. And then if we're dividing by a negative exponent, that exponent becomes positive. So our half-life is, sorry, that's weird in, 16.9 minutes. Okay, so just following the equations, plugging things in, the math is not too difficult here. For the question on the bottom, we have the isomerization of cyclopropane to propylene is a first order process with a half-life of 19 minutes at 500 degrees Celsius. The time it takes for the partial pressure of cyclopropane to decrease from 1 to 0.125 atmospheres at 500 degrees Celsius is closest to. So for this one, we need to figure out how many half-lives occurred. So we're starting at 1.0 and we're ending at 0.125. The first half-life, it's half of the amount, so we go to 0.5. Second half-life is half of that amount, so half of 0.5 is 0.25. The third half-life is half of that amount, which is what we want, the 0.125. So we know we have 3 half-lives, and we know a single half-life is 19 minutes. So 3 times the 19 minutes gives us 57 minutes. Our answer there is B. Okay, so it's an example working forward and an example working backwards. Only one of them you actually need the equation though. All right, that is the end of the notes for kinetics. All right, some of these topics can be confusing, especially that fast equilibrium. Make sure you understand that. If you need help with it, ask questions. Come into tutoring, ask during class, do what you need to do. All right, work through that practice packet. That'll really help you to work out those rate reaction, the rate laws. But if you have any questions, ask them. All right, I will see you in class. Have a great day.